Set recording. Yeah. Hello everyone. Today, in today's seminar, we have a talk by Subhasree on quantum walks and its applications. Subhasree is a PhD student at the Algorithms and Complexity Group at CWI in Amsterdam and QSoft. He currently works under the guidance of Professor Harry Berman on conditional quantum time lower bounds. And yeah, so today she'll be presenting like few basics of quantum walk algorithms and their applications. Yeah, so you can start the talk.
Thank you, Anirudh. Hi, so let me begin. Okay. Now, before we go into quantum walks, let's start about classical random walks. Okay. So, what is the problem? We have a say graph of n vertices, and we are told that epsilon fraction of these graphs, vertices, are marked. Okay. Now we need to find a marked vertex. So how do we do? So you can start with some random, like with some specific vertex y. Okay. Check if it's marked. Sorry about that. If it's not, then look for its neighbor. And make that neighbor as y. And repeat the same process. Okay. Now this process is like, it's a random walk. So you kind of have a graph, you know there are some marked vertices, and you have some neighbors. You just randomly pick some neighbor and then check if it is marked. If it is not, then again do the same thing on this vertex. Okay. Now let's see the complexity of such a algorithm. For the purpose of this talk, we are going to assume certain properties of graph. First property is we're going to assume that it's an undirected graph. We're going to assume that it's connected. We are also going to assume that it is d-regular, which means every vertex will have d neighbors, exactly d neighbors, okay? And no self loops. And fourth thing we're going to assume is it's non-bipartite. We will see why these properties are important for us to assume in a short while, okay? Now, what I'm going to show is like, now consider an adjacency, adjacency matrix P of size n cross n, okay? But this adjacency matrix is going to be normalized. What do I mean by that? So if I have an element of this matrix, it is going to be 1 by d if xy is an edge in the graph. It's going to be 0 otherwise. Okay. Now you understand why we need this requirement that it's going to be d-regular. We want some constrictions on these values. Okay. Yeah. Now the claim is this P is going to be analogous to a walk on the graph. Like application of P is going to be a walk on the graph. I'll show you how. Now, imagine you took a vector v, okay, which is 0 on all elements. It's a vector of size n cross 1, okay, and it is going to be 1 at say y'th coordinate here. If I do PV and then I take this element x, this is going to be 1 by d if xy is an edge. And it is going to be 0 otherwise. So what it shows is the application of P on vector once kind of gives a probability distribution of on all the neighbors of y, right? So we have like and from concentration on one element, we have moved to a vector where where the distribution has spanned over some neighbors of these elements. Okay. Now what we are going to claim is for every such P, we have a K such that Pk on V, no matter what the V is, will converge to a uniform distribution on all the vertices. Okay, that is what the claim is, and we're going to prove the claim. Now, when I said no matter what V is, V doesn't have to be concentrated like in this case. It can be it can start with any probability distribution on say P1, P2, Pn on all these vertices, okay? Yeah, now let's see why, okay? Let's see. So now the first thing that we're going to show is this. Look at this vector u, which is 1 by n, and it has all the other elements 1, okay? Clearly, if you just check, pu would be u. So we can say u is an eigenvector with eigenvalue 1, right? Okay. Now let's understand the other eigenvalues of P. And by understanding the other eigenvalues of P, what we are actually understanding is some property of the graph that is called the spectral property of the graph. Right? Because this P was specific to how the G was. Okay. Now, because P is a stochastic matrix, like it preserves the distribution on the vector, all its eigenvalues are going to be less than equal to 1. Okay. So we have the largest eigenvalue, this as 1, and we are going to order all these eigenvalues in this way. Okay. Now, what can we say about the eigenvectors? So we know that V1 is actually RU, the uniform distribution over all the elements, right? So this we know. And we know one more thing, that is for all these VIs where I is greater than equal to 2, I mean all the other vectors, the elements in Vi should sum up to 0. Okay. So if I want to say this, why? Because look, these are eigenvectors, right? So they all have to be orthonormal to the uniform distribution. So the only way they're going to be orthonormal to uniform distribution is when the summation of their individual elements is going to be 0. Okay. But why is that important? Because now we're going to prove this claim that I made here. I'm going to prove this claim and I'm going to use that fact there. Okay. So, okay, now consider PKV for some starting vector V. Okay, we are going to consider this. Now let me write V as a like in this basis, in the basis of these eigenvectors, right? I can do that. Then my PKV is going to be this This is simple. And by linearity, we will have this alpha I, pk, vi, right? Now, because these are eigenvectors of P, I can make this as an alpha I, lambda I, k, vi. So this is also clear. Now, this will be actually alpha 1 into lambda 1 into v1 plus right? Okay. Now this we saw was 1 because that was the uniform distribution, and this was u. And my claim is that alpha 1 is also going to be u. Alpha 1 is also going to be 1, okay? That's because yeah. And that is because, see, whatever pk is on v, it's going to give a probability distribution in the end, okay? And the summation of all these elements, say, so it gave some vector. We know that all the values in this vector is going to add up to 1, okay? Now we know the values in u also add up to 1. But actually, the values here, if you add them, they'll all be 0 because the elements of vi are going to add up to 0. So none of these is going to affect. That's why alpha 1 has to be 1. Okay? That's the reason. So now what we see is this pkv minus u is this quantity. Okay. And I'm not going to go into detail of this calculation, the next calculation, but using some linear algebra, you can prove that this is upper bounded by 1 minus delta whole power 2k, okay? Where delta is called the spectral gap, okay? Now, the actual definition of delta is the largest eigenvalue, that is lambda 1, minus max of modulus of the other eigenvalues, okay? So, and the reason why we took these assumptions about these, we had these constraints about the graph was because if you assume the graph is connected, you have the lambda 2 less than equal to 1. And when you assume the graph is not bipartite, you have this lambda n greater than equal to 1. So you have all these lambdas belonging to -1, like it's ranging between 1 and -1. So this is going to be one important ingredient in proving why this square norm is less than this quantity, okay? Anyway, now if you kind of set this, so now you know that this pkv is going to converge to u, and you can decide how much convergence you want. Say you want this to converge to eta, then by Taylor expansion you can see that like 2k, so you have log of 1 minus delta will be equal to log of eta, and this by Taylor expansion is almost equal to minus delta. So you have k as order log of 1 by eta. This is not n, this is eta by delta, okay? So by choosing a particular eta, you can always you can always see how many times you have to do this walk so that it converges to uniform distribution, okay? Now, once it converges to uniform distribution, you don't have to apply P anymore because that will just keep you in the uniform distribution, right? Remember, PU was going to be equal to U. So no matter how many times you do this, it's going to be still equal to U. So you can just stop after this many applications of P, okay? Now, but what have you done? So what you have done is you have now brought your search to a state no matter what you like, what step you take, you will pick a vertex randomly. Like in like so if I'm here, I might pick a neighbor also with the same probability, but I might pick neighbor's neighbor also in the same probability. Like it's you're in that state. Okay. So, and you know that there are epsilon of marked elements. So the probability that you pick is epsilon. So with 1 by epsilon um, expected number of runs of this whole algorithm, you are going to hit a marked element. So now let's see the complexity. So, and how do you know whether an element is marked? You just check, okay? So now say the cost to check a mark element is C, okay? Now say the cost of applying this P is U. Then what you have is, you have 1 by, so you apply this K times, so you have around 1 by delta number of times, right? Because you are doing this K times and K is around order 1 by delta applications of U, and you have checking cost as C. And this whole process you do 1 by epsilon number of times, because that's the the probability of hitting a marked element is epsilon. And then the other last thing that you have is the setup cost. In our case, like in the classical case, it doesn't matter too much, but the setup cost is on what V you started with. Like what was the initial distribution that you started with, okay? So the cost of setting up this V. So this is the complexity of this classical random walk. Okay, and we will put this as equation 1. Now what I'm going to show is, in the quantum case, we can bring this down to proved 2 s plus 1 by root over epsilon C plus 1 by root over delta U. Okay, we're gonna achieve this. Any questions as of now? Okay, I'm assuming not, and I'll continue. Okay. Now, some things that we're going to do differently from the classical walk. Now, remember, in the classical walk algorithm, we always were concerned with some vertex, and the walk took us to a neighboring vertex. Okay. And we were also having operation P, which was distribution preserving. Okay. And anything else that we're going to do different? Okay. I will add if I figure out something else. Okay. But in the quantum case, we're going to do something a little different. Our state at any point of time is not going to be a single vertex, but it is going to be a vertex and the previous vertex. So we are going to keep 2 registers, one for the current vertex and one for the previous vertex. And instead of a distribution preserving matrix, we would like a unitary, which will be a norm preserving matrix. Okay, so we'll have something which is related to P, but it will be not exactly P. Okay, so these are the 2 things that we're going to do differently. So now some things I will define. Okay, so now imagine you start with a quantum state. So you have first register to store a vertex X, and the second register is going to store a neighbor to this vertex X. Okay, and we call a basis state is good if my X is marked, bad otherwise. Okay. Now I'm going to define something else, that is, I will define P of X as the uniform distribution of my neighbors of x. In our case, because we were looking at a d-regular graph, it's going to be 1 by root d y, where y is going to be a neighbor of x, okay? Or I can just write xy is an edge, sorry. Cool, okay. Now, yeah. So I'm going to define something called a good state, and I'm going to define something called a bad state, okay? Now, if people who are familiar with this Grover's algorithm, they might be already guessing where we are going with this. But for people who are not, I will try to keep it as simple as possible. Let's see. So my good state is going to be a normalized vector of all these elements that are marked. Assume that M is a set of marked elements. So this is going to be all my good states with its neighbor. So all my good states with the superposition of all its neighbors. Okay, so this is what it is. But I need to normalize it. So I need to put, because I know there are like total of size of M. So I just put this factor there, okay? And my bad state is going to be 1 by this, where X doesn't belong to M and it is X, Px. Okay? This is my bad state. Now, please don't get boggled by these values. Simple calculation will lead you to that, okay? The constants. Now, and to like another observation will be, look at the space, look at this vector, good vector, and the bad vector. They are going to be orthogonal to each other, okay? Because this was what my basis state was. This was my basis state, right? And whenever I'm going to have different x's, because obviously if x is in M, an x from here is not going to be in M. So they're going to be different states and they're going to be orthogonal, okay? Yeah. Now we are going to take a state U, which is uniform superposition of all the states. So we're going to say U is put over N, all vertices, this P of X. Now, clearly you can write U as 1 by root N, X belonging to M, X Px, plus 1 by root N, X not belonging to M, X Px, right? I'm just writing all the elements because this belongs to N, right? So this can be written as right? So yeah, and you see square of this and square of this actually becomes 1. So I can take this as some sine theta and this as some cos theta. But if you remember my epsilon, that was the number of marked elements itself was M by N, right? Actually, it was this. Oh, I forgot to put this. Sorry about that. Yeah. Anywhere else I need to do? No. Okay. Yeah. So we have our theta is actually sine inverse of this. Okay. Yeah. Now we're going to see why all this is relevant. That's because look at this statement. Our U is a like this is this G is going to be orthonormal to this B. So my U can be expressed as sine theta G and cos theta B, right? So remember this diagram where I had G in this way, I had B here, okay? And I now know that my u is also in the same plane as G and B. Okay. And what would I want to achieve? I would want to find a marked element, right? And my state, I'm starting with a state U, and I want to find actually a marked element, which is actually like any of these elements in G. So if I have an algorithm where I can kind of rotate this U to this G and then make a measurement, then I'm bound to collapse on one of these basis states. This is our aim right now. Okay, so that would mean that I have found the marked element. Now, what more do we know? We know that the sine theta is with G and cos theta is with B, right? So theta is this angle. Okay. Now, if we have a way to say rotate this U about this B, and then the new state, if we can rotate about U again, if we can make such a unitary, then we are actually implementing Grover like algorithm. Okay. So now what do we do? So we do the following, and look at this. If I am having a, I need these ingredients. I need the following: a unitary that rotates any state about this vector B, and unitary that rotates any state, and I mean any state in this plane, okay, about this uniform distribution U, okay. Then what do we get? So if I make this kind of rotation, I'm effectively changing the angle. So this is my final state after one such rotation by 2 theta. Okay. So if I make, and if I do this k times, then I'm effectively getting this out. Okay. Now if my k is approximately, so if my k is pi theta by pi by 4, which is approximately this many number of runs, I can, because see what I'm doing here is I'm trying to make this amplitude as big as possible. Like I'm getting this value close to pi by 2 so that this amplitude becomes 1 and there is no amplitude on the bad state. So when I measure this, I'm going to collapse on one of these basis states, which are marked, because that's how I define these good states. Okay. And I can achieve this if I fix my k parameter to pi by 4 theta. And because theta was this, which is very close to 1 by root epsilon. Okay. Can get a marked element. Okay. Now, so we have to implement these two things. We have to implement a rotation about this vector B, and we have to implement a rotation about this other vector U. Okay. Now, rotation about B is simple. Okay. So imagine if I tell you that, okay, give me a rotation about some vector, say T or something, and like I just tell you, give me a rotation about this. So what do? You can always write an arbitrary vector in this form, right? Alpha T perpendicular to that, and say beta T, where alpha mod square and beta mod square is equal to 1. And a rotation about T would, say this is a rotation on about T, would give me a phase of -1 for the vector that is perpendicular to B. And for the vector that is not perpendicular to B, that is like T, it should not give me any phase. This is what my rotation would do, right? So here also, we are doing the same thing. Rotation about B just means finding whether an element is marked. That's all, okay? And we are going to assume that finding whether an element is marked or not just takes checking cost C, okay? We don't have to fill it in now. we're just going to assume some value C. Okay? Now the tricky part is, how do we implement a rotation about U? So let's do that, okay? Oh, actually the word is reflection about you. Like I kept saying rotation about you. You can say reflection through you or something like that, okay? Yeah, now let's do that. Now, some like we'll have to digress a bit. Okay? Now imagine this is a subspace spanned by the vectors x and px, where x is all vertices, okay? And imagine this curly B is a subspace spanned by P, Y, and Y, where Y are all vertices. So you see the difference, right? There's like, this is spanned by X and superposition of its neighbors. Here it is superposition of Y and then Y. There's a difference, okay? Now we define two operations. We call reflection of this A as a unitary that takes any vector which is in this, say V is inside this subspace, then it takes 2V, and anything for V in the subspace, anything perpendicular to the subspace, it will give a -1 phase. Similarly, we define operations for B as well. Don't get scared by these things now. We'll see how easily you can actually implement this. Oh, sorry. Yeah. Okay. And the way we can implement our unitary, like our walk step, is going to be W of P, which is reflection of B into reflection of A, like these two unitaries. Okay. Now we'll see how we can implement them actually very easily. Now look at now for once, consider this operation. We start with the vertex. We start with initial 0 state, and we get x and p of x. Okay. Now this you can implement classically also, right? You're only getting basically informations of all the neighbors. So you can do it quantumly also by putting a reverse condition. So you have a unitary which can take x and empty register to, so unitary 1, x and this px. Okay. Now imagine, because I have unitary u1, I will also have unitary like inverse of this unitary. Okay. Now imagine if I what if I do this? Whatever my state psi b, which is coming from my algorithm, I apply u1 inverse. Okay. And some state would come out for me, right? Some psi and some psi prime will come out for me, which will have 2 registers, right? Now I check whether my second register, whether this part of the register is 0 or not. If it is 0, then I put u1. Okay. If it is not 0, I put minus u1. Like I put a phase. So what I have effectively done is I have actually implemented this reflection A wala operation by doing this. Why? Look at this. So if my state was some form of like this kind of state, which was in the subspace A, then I would have gone back to this state because I'm putting U1 inverse first. And then I would check if this register is 0 or not. And because I would get this register 0, I will put U1 again. So I'm putting no phase. So I will get back my this this state. Okay. So for every element that is in the subspace A, I don't get a phase in that case. Okay. But if it was something else, then I would put U inverse, and my second register is going to be some garbage value. That means which is not 0. So I am putting a -1 phase again. So I am doing this operation in that case. And similarly, I can implement this reflection B by doing the following, that is sum U2, which is taking Py to Y. Okay. So I'll do the same thing again. Whatever says some states came psi to me, I will do U2 inverse and check for the first register in this case. 0. You just do U2 in, if not 0, you do minus U2. Okay, same thing. So here you have implemented reflection about B. Okay, so you like I showed you existence of unitaries that can actually do what reflection of A and B were doing. Now, if you remember, my WP was a unitary which was just reflection of this B subspace and this, right? Now this WP on my on my initial state, this which was superposition of all these vertices, and like this is my initial state, right? So if you notice that WP on U is going to be just U, it is not going to be anything different. You can check that because of the way this XPX and the way this subspace A and subspace B is defined. So there's one common vector to them, that is actually U. So reflection on this U is going to give me U. And then reflection B on U is also going to give me U. That's a tiny calculation. And you will see that this is actually an eigenvector of this unitary U with the eigenvalue 1. Okay. Oh, I don't know yeah, eigenvalue 1. Okay. Now, remember, we implemented this as a unitary because we saw the existence of two unitaries. So we know this is a unitary. And now our earlier goal was to actually implement a reflection about U, right? So we wanted to implement a rotation about U, which means for any state, which is this plus U perp, where alpha squared plus beta squared equals to 1. We want that this stays as we want this this state to become this, right? That is what we want to do about this unitary about U. Okay. Now, and what do I know about this? I know that this U is an eigenvector of WP. Okay. So all I need to know now is whether I'm getting a psi, suppose whatever psi I get, by linearity, I need to know whether right now I'm having this state or I'm having this state. Then if I can distinguish between what state I'm getting, then I can always put a phase, right? That is my intention. And for that, we are going to use a very interesting trick called, any guesses? No, okay. Phase estimation. And this phase is like, it's a digression, but it's a very interesting digression because you can know a lot about which vector you are applying by this phase estimation. Now let's see what is phase estimation. Okay. Suppose I tell you, I give you black box access to some unitary R. Okay. And what do I mean by black box access? I don't know the contents, like I don't know which gates are there in R, but I'm allowed to use R in my circuit. That is a black box access. Like I don't know whether it has ands or like where all it has ands and nots and all that I don't know. But someone is telling me, okay, I'm going to give you R in the circuit. Okay, I'm allowed that. And phase estimation is, if I'm given a vector psi, which is an eigenvector of R, then I can estimate the eigenvalue. Okay. Now, I'm told that I'm given a unitary R. That means my eigenvalues of R are going to be of the form e power I theta, right? Whatever the dimension is. Because that's a property of unitary, right? Okay. Now, if I'm given, so every eigenvector will have a corresponding eigenvalue. So if I'm given some psi, which is an eigenvector of R, and I'm allowed to use some ancilla states, then I can apply some, like I can apply this phase estimation algorithm, which lets me apply R a number of times. Then I can get back the state, and I can also get an estimate of this theta j, which is the eigenvalue for this particular vector. Now, why is that important? But if we are allowed to do that, why is that important? Is because remember, we want to actually have a reflection about U. And now we have access to a unitary. This is WP, which we define. Okay, that's a unitary which we can always use. And I know the eigenvalue corresponding to this U was 1, which means my theta j was 0, right? Yeah. Now, if I have any other vector, say U perp, that means this phase estimation algorithm is going to give me some other theta value, right? Because like, so whatever input comes into this, if I can just put it in the phase estimation algorithm, say if I got U, I'm going to get 0 here. But if I got some U perp, then I should get some other theta value. So I can always use this phase estimation algorithm and estimate whether my vector that is going is U or U perp. And whenever I'm conditioned on that, whether it is 0 or not, I can always put a phase. So if it is 0, I don't put a phase. If it is non-zero quantity, then I put a phase. Okay. But how many, like, and this estimate is not, see, it's not like you can have infinite precision, right? So this, the number of runs that are required of this unitary is going to depend on what is the estimate that you require. This is now what is going to happen. Like we're going to now come back to the algorithm. We're going to see, okay, so now what do we have? We have yeah, so we have about 1 by root epsilon number of runs of reflection about B and reflection about U, right? So we have this. And then reflection about B was just checking whether a vertex was marked or not. So we just put C. Now reflection about U was going to be some number of times. So I'm going to put I'm going to fill this up. Some number of times application of this WP, because we were going to use this phase estimation algorithm to understand how many, like whether we are going to put a -1 phase or +1 phase, right? And this is my walk step. I said, right? Remember in the beginning, I said this is analogous to what P was in the classical case. This was my walk step. And say the walk step takes U amount of time, update time. Then I'm going to see how many times I need to run this. I'm going to still fill that up, okay? And plus the setup cost, which was like how costly is it to make this uniform superposition state to make. Okay. Yeah. Now you already see there is a change in the value here because the classical one was S plus 1 by epsilon C plus 1 by delta U. And I'm going to show that this value is going to be 1 by this term. Now, remember, I told you to estimate the phase, we need to know to what precision we need to estimate. Okay. Now, if you recall, P had certain property of this these P spectrum. Okay, spectrum lambda 1 equals to 1, which is greater than or equal to lambda 2, lambda n, and we knew all our lambda i's for I greater than or equal to 2. We had lambda I belonging to, sorry, this one and 1. Okay. Now, I am not going to show with calculation, but WP happens to have its eigenvalues of the form. One second. So the so this has the eigenvalue of the form e power I theta j, where my my lambda j modulus is equals to cos theta j. So this I'm not going to calculate here. Actually, I don't know how to calculate. Like I don't know how they got this relationship, but there's a relationship with these two. Okay. Now we know for lambda 1, my theta 1, for lambda 1 equals to 1, my theta 1 is going to be 0. This much is clear. Okay. And because of the other constraints that we put in this P matrix, remember we said the graph was not bipartite, the graph was connected, and like we put a bunch of conditions. Because of those conditions, we also know, and because of this relationship, we know my other thetas are going to be greater than or equal to 2 delta, where delta was a spectral gap of this graph G, or this adjacency matrix P. Okay, so this relation is known. Okay? So if my theta is 0, that is fine. But otherwise, I am promised that my theta is going to be greater than 2 delta. So if I guess, if I'm able to estimate theta to a precision of delta by 2, then I can distinguish, right? I can distinguish their corresponding eigenvectors. And that phase estimation algorithm, I had told you, phase estimation algo, like the number of times you access the unitary R depends on the precision. So if I want, and the way it depends is, so if I want a precision of this, then I need to apply this R, or in our case, the WP unitary 1 by root delta times. Then I can get a value of theta to this precision. So that's why the number of times I do my quantum walk is this 1 by root over delta. Okay. So clearly we saw now in quantum case complexity drops down to S setup cost plus what is it, 1 by root over epsilon checking cost plus 1 by root over delta update cost. Cool. Any questions until now? Then let's discuss the first application. And I think we will stop also after the first application, okay? We will see the query complexity of collision problem. Okay. For people who are not familiar with the concept of query complexity, is it's like, suppose you have some input, like say in this case I have x. Okay, let me first explain the collision problem, then I can explain what you mean by the query complexity of the collision problem. That will be better. Okay, so a collision problem is you have say n elements, x1, x2, x n. Okay, is there a xi equal to xj such that I is not equal to j? Basically, all it wants to know if there exists some element which repeats. Okay. Now, clearly, we have a linear, n log n time algorithm, right? You can just first sort the entire list, and then you can check for neighbors, and that also will take linear time. So sorting takes this much. 1 second. Sorting takes this much. Then in linear amount of time, you can check neighbors. So you have this n log n algorithm. Okay. But can we do, like, can we get down that below n, say in terms of query complexity? Now, what is query complexity? So you don't care about how much time it takes, but you care about how many inputs you accessed. Now, say someone tells you that there are n elements, but they don't give you all the n elements. But the only cost you pay is when you ask them, okay, what is x, say 5? Then they give you the answer of what x5 value is. Okay, so that will be one query. Now, if I say, okay, we need only query complexity, clearly any computation on such a model is going to be at max n, right? You're not going to, like, once asked, you're not going to ask that value again. So it's not, the query complexity of any function is not going to go beyond n, but it can be sublinear. And in our case, we will show in the quantum case that query complexity of collision can be done in n power 2 by 3 queries, which, by the way, is tight because there's a matching lower bound also, which is a result of some other paper, which I don't know yet how to prove. Yeah, I don't know how to prove that yet. Okay. So let's discuss this algorithm. So and the proof for query complexity of collision taking this much is using quantum walk. Okay, we'll see. Yeah. Okay. Now, imagine something called a Johnson graph. Johnson's graph. Here, the graph is of this kind. So when you have this graph parameterized by two things. You have n and r. So you have vertices that are labeled as R subset of these n indices. Meaning, I will have, so in total, the number of vertices is going to be n choose R. Okay. So you imagine this graph with so many vertices, okay? And you are going to only have edges in the graph when, so if I had, say, n was 5 and say R was 3, then I will have like my subsets, right? I'll have 1, 2, 3, 1, 2, 4, and so on. I'll have so many, like so many vertices I'll have, okay? And I'm going to only put edges when my, the set that, so, okay, let me put it this way. So I'm going to label every vertex with a set Si, where Si is a R subset of N, okay? Yeah. So I'm going to put an edge between Si and Sj if and only if edge exists between F and Z, if and only if they differ by, like, they have exactly R minus 1 elements in common, okay? So if Si intersecting S, oh, not V of this thing, sorry. If and only if my Si intersecting Sj has R minus 1 elements, which means there'll be one index in this set Si which will be taken out and replaced by some other element in this set, right? Okay. Now, so this graph is huge, okay? But the best part of this graph is the spectral graph for the spectral, the delta value for this kind of graph is very low for such graph. And my delta, what I'm talking about is in the context of this delta, the spectral gap of this P and all that. Okay. Low, okay? Now imagine, so you have these kind of vertices and we want to know query complexity of this collision problem, right? So what we do is, for every vertex of this kind, we are going to keep a register which will query all the values of indices in Si. So if my Si had this set 1, 2, and 3, suppose, for example, then my my register is going to have x1 value, x2 value, and x3 value explicitly. Okay. So at any point of time, if and because I know my Si is going to be exactly equal to R, I'm going to query only R elements. Okay. Now, oh, another, when I said this delta value is relatively low for these graphs, the delta value is actually equal to almost 1 by R. It's very close to 1 by R for a graph like this, okay? Yeah. So now what else do I have? Yeah. So in such a setup, okay, another thing. Now we want to know whether there's a collision in this n elements, right? So we are gonna also calculate what will the epsilon value be for such kind of a graph. Now remember, epsilon was defined as fraction of marked elements. So if my problem statement, if my problem instance, sorry, not statement, problem instance, that is like I'm given x1, x2 up to xn, say had one collision. Like I'm assuming that, let's say my had one collision or no collision. Okay. Oh yeah, I forgot to tell you. Okay. So I'm going to do one more thing. That is, I will call these vertices marked if they have a collision within them. In the sense of, like, see, my vertices are going to be R subset of these indices, right? And I'm going to query them at one point where I'm explicitly going to get the values of all R elements. Now, if there exists a collision in my input instance, that means there will be a collision in one of these vertices. Like they will be present in some subset of n, which means it will be present in one of the vertices. And if it is in whichever vertex it's present, I'm going to mark them. Okay. And because so my epsilon is going to be very close to, that's also easy to calculate. It's just a probability calculation. It's going to be very close to r by n whole square. Okay. So now I know my number of marked vertices, if there is one collision, is this much. And I'll assume that there's only one collision. Okay. This kind of assumption is fine because there are tricks to check for different epsilon values. And I'm not entirely clear with the tricks yet, but you can just keep checking as if there are different number of collisions, and you can run this algorithm. And the blow up is not too much. It's very less. So that's allowed. Okay. So now we have delta was equal to, I think, 1 by r, right? What did I write? Yeah. And we had epsilon, which is equal to r by n whole square. So my 1 by root delta is going to be root r, right? And my 1 by root epsilon is going to be n by r. Now we plug it in our quantum complexity. We had already calculated the complexity of quantum random walks. We had seen it is setup cost plus 1 by root epsilon, checking cost, whether an element is marked or not, and 1 by root delta of this update cost. Okay. Now, what is my setup cost? My setup cost here will be to, remember, my setup cost was for this vector, which was uniform superposition of all edges. Remember, it was actually, it was 1 by root n x and px, right? So it is kind of like uniform superposition of all edges here. Okay. Now, for me, I'm only interested in the query complexity, right? So my query so if I want to write the state, so I want to write my vector x, my vector p of x, but for every x, I want to explicitly write all the queries. And for every this also, I want to explicitly write all the queries. So that is going to cost me r plus 1 queries. So my setup cost is going to be this many queries. Why r plus 1? So for every x, you're going to query r elements. But for p of x, you're not going to query again. You know that the edge, like the neighbor, will only exist if they differ by one element. So that is the extra element that you're going to query. And once you have queried, you can go to and fro, like you can go back and forth on the queries and you can do any computation. But that doesn't count because we are not asking for the value again. Like we have copied the value. So my setup cost is r plus 1. Okay. My checking cost is going to be 0 queries, because what was I always checking? I was always checking whether vertex is marked or not. But the moment I have queried the vertex already, whether there exists a collision, I can always check internally. I don't have to like ask for the value again. So it is going to cost me 0 queries. But my update is going to be constant number of queries. And that is because, remember, my update was one application of WP, which was reflection about B, this B subspace, and another reflection about A subspace, which we had seen was the inverse unitary of this. This reflection about the A subspace was something of this form, right? It was x 0 to x p of x. This was my unitary, and it was a reflection. It was the opposite reflection, and this was also similar. Okay. So yeah, here also you're only going to require one additional information, because see, the x, like look at this unitary. How many queries will it cost? it'll cost me one extra query because I already have the entire information about X and the values. So to get the neighbors, and I can do this in superposition. So I'm going to just need one extra value here. And I do this twice. Oh, actually this will require, yeah. So it will require actually 4 queries. So plugging this back into this formula, what do I get? I get, so the formula is this, 1 by root epsilon C plus 1 by root delta U. So plugging back into this formula, I get R plus 1 plus 1 by epsilon was how much? N by R into zero plus, this was I think root R, if I'm not wrong. Yeah. And update cost was constant. So I'm just going to ignore it. So we have like R plus N by root R, right? This is my complexity. And you want to minimize the number of queries. You want to minimize the number of queries. So you choose an R such that R is equal to, like this kind of gets balanced, like this term and this term are balanced. So you have R 3 by 2 is equal to N. I'm sorry guys, I mean the capital N here. I'm sorry guys and girls. Okay, so we have R equals to N 2 by 3 queries. So you plug that back here in, you know that you will need order this many queries to solve collision problem quantum D. Yeah. This is how much I wanted to speak. So I'm done. I would like to take questions now.
Yeah, are there any questions? If not, I'll be stopping the recording.
Yeah, sure.
Okay, nobody's asking. So yeah, thank you everyone for attending, and thanks Subhasree for giving this wonderful talk. Can find
You're
a
welcome.
time for this.